All right, welcome back. Let me begin the lecture just by reminding you briefly where I stopped last time. I was looking at an application of effective field theory to a case of flavor physics. Today's flavor is B. And the idea was to look at this type of processes where you, in a machine, an E plus E minus machine, where you can generate B quarks, but yet not have enough energy to generate a top quark. And in particular, I was going to look at the case where you generate an odd number of B quarks. And that is because such a process is suppressed by very small CKM mixing angles. And so it might provide a window of opportunity where the new physics effects might shine through. These are very peculiar flavor-changing new physics effects, but I think it serves as an illustration of using an accidental, or apparently accidental as far as we know, suppression of standard model effects to identify a reaction where new physics might be easier to find. And so it came down to calculating this cross-section. This is a theoretician versions of a not naive cross-section in that it includes the possibility of misidentifying jets of other quarks for B quark jets and for missing some B quark jets. And it involves a certain amount, three experimentally derivable quantities, the efficiencies and the probabilities of mistaking C quarks and light quarks for B quark. And where I last ended with presenting to you my condition for success in identifying a new physics effect in this equation that's summarized by this equation, in which the measured number of events with KB jets and J total jets, with K odd, is larger than the standard model by 3 sigma, that I call delta. I didn't use sigma here because sigma is used for the cross-section, and I didn't want to repeat the letter. And so the error, 3 sigma, the error is composed of a statistical, systematic, and theoretical error. The theoretical error is generated by QCD effects I did not include, but one could, and thereby this would be reduced, but I didn't do that. A systematic error that depends on the experiment, and it's again something the experiment can provide, and a statistical error that is the usual square root of n effect from statistics. And I've added them in quadrature, which embodies the assumption that these errors are uncorrelated. All this is open to discussion, but let me just continue along this line with these assumptions. And then I introduced a type of new physics. This is, as I mentioned, not the only new physics you can probe using this reaction, but I chose this one. It will contain flavor changing in the quark sector. In the lepton sector, I did not include such flavor changing because that wouldn't be useful for my machine, which is an E plus E minus machine. E plus and E minus are both in the first generation, and therefore these leptons will be in the first generation. The quarks will be one in the third generation and the other in one of the 2 remaining. This can be generated by, as I say here, a Z prime, and as I discussed last time, also by an appropriate leptoquark, vector leptoquark. And here are the results. These are the choices for the various errors and various probabilities for misidentifying them. This thing comes from the people in LEP, and the systematic error as well, the theoretical error we estimated or guesstimated by looking at possible QCD corrections. And the result here is for LEP, which was this first line here, and various identities, you get the 3 sigma limits on lambda in TeV. So with a 200 GeV machine, you can probe new physics up to a scale of about 700 GeV, and so on. For one TeV machine and a significantly enhanced luminosity, you can probe new physics up to about 4 times the center of mass energy, which is a reasonable reach. So the thing to get, the numbers here are not as important as the following thing, that if you have a process where the standard model is naturally suppressed, your collider reach will be significantly enhanced beyond the center of mass energy in probing new physics. This disappears once the standard model effects are very large, because in that case, you need an enormous amount of statistics, which in reality will not be available to you. And this is the same type of results in graphs for a half TeV collider and a 1 TeV collider for different kinds of new physics. And this is the area that can be probed depending on I apologize. This should be epsilon b, not TB. Epsilon b, not TB. Okay. So this is the example. Okay. All right. The next step would be to go through formal developments. But before that, I had this nagging doubt and asked around, and it was confirmed that I was less than clear when I talked about the strongly interacting version of the effective theory in my presentation of the various estimates of the coefficients. And if I would like to ask your patience in my going back to that and presenting to you in a little bit more detail how I derive what I call the naive dimensional analysis estimate of the operator coefficients. I will use the board for that effect. And so okay. So I remind you, what I wanted to do was the following. I was starting with operators of the form lambda of B, thank you, lambda of B and F, phi over lambda phi to the B, psi over lambda psi to the F, d over lambda to the d. And I'm going to, and this is symbolic. So what I'm doing effectively is I'm associating a scale of new physics, lambda phi with the scalars, or boson, with the scalars, right? A different scale in principle with the fermions, a different scale in principle with the derivatives. And I am going to try to put, and I'm allowing for an overall coupling constant in front that depends on the number of boson and fermion fields. And I am going to study the possible effects of this type of operators, under the condition that the theory is strongly coupled. And what I mean by strongly coupled is that every time I do a radiative correction, the effect will be of the same order as the tree-level effect. Okay, so the first thing I want to do is look at the coefficient in front. That's the first one I want to do. I'm going to do half the calculation because the other half is straightforward and just a repetition. What I'm going to do is consider an operator that has 2 more boson fields, 2 more, for a reason you'll see in a minute. So I'm going to consider the operator O prime, which has 2 more B's, B plus 2, and then the same number of fermions, and the same number of derivatives. And what I'm going to do is I am going to consider a Feynman graph. I have many colors, so I'm going to use them all. Okay, so I'm going to consider a Feynman graph that has a number of external legs in blue, and such that my operator O contributes to it. So somehow the operator O is one of the vertices inside this object here. Okay? It could be that these lines could be bosonic or fermionic. It could be that some of these lines correspond to some of the fields there. It doesn't matter. And what I want to do now is consider a related graph that involves my O prime here. Okay? And so this graph will look exactly the same. Exactly the same. So this is a graph that will contain O prime. So, oh, sorry. I already screwed up. Okay. Green. All right. It has the same number of external legs, but now my O prime, which contributes to it, my O prime that contributes to it has two additional bosons to play with. And what I'm going to do with those two bosons, I'm going to take them out and join them. I'm going to assume that they can be joined. And so I have an additional pair of bosons that I will join. Oops. So I have the same graph I had before with an additional tadpole. That's the only thing I got. An additional tadpole. This is a radiative correction to this guy. By the strong coupling assumption, the effect of this guy will be of the same order as this guy. Okay? But this I can calculate, I can estimate. And that's why this is called naive. I'm not going to calculate anything. I'm just going to estimate everything. Okay, so what is the difference between this guy and this guy? It will be the following factor. This guy has a factor of lambda BF and stuff in front of it, because I told you this guy is inside. This guy has a factor of lambda B plus 2 and F, has an additional 2 powers of 1 over lambda phi squared from here, and it has a loop. For the loop, I am going to simply replace momenta by lambda. I am tacitly assuming that because this scale lambda is associated with a derivative, it is then associated with momenta. It will serve as a kind of cutoff regulator for all integrals in all subsequent estimates. So what is that? Well, the tadpole gives me 1 over lambda squared for the propagator, lambda to the 4th for the loop integration, and my standard punishing factor of 1 over 16 pi squared because I have a loop. And the result from substituting this instead of this should not change the order of the expression. That is, since this is of the same order as this has to be of the same order as this. And I will stop putting a squiggly line. I'll just put an equal sign. But please remember, these are all estimates. So I have this, that lambda BF is equal to lambda squared over lambda phi squared. Sorry. I don't want to write this. I want to write it with a 4 pi in front. 4 pi lambda phi all squared lambda b plus 2 f. So I've related the coupling constant with 2 extra boson lines to the one with 2 fewer, to the original one. And I can keep on doing this with more and more things. And so I can solve this for lambda b. And you get the following thing. Lambda b and f is equal to of 2 and f. And now I can do the same thing for the fermions, but I will not bore you with that. I will just tell you the result. The only difference is, to remember, is that the operator in question, when you add a fermion, well, it has a lambda psi instead of lambda phi. The propagator, however, has 1 over lambda, because the propagator is 1 over p slash minus m. It's not 1 over p squared minus m squared. So there will be, instead of a 1 over lambda squared from the propagator, I should say, no, this is propagator. And this is the loop integral. For the fermions, there will be a 1 over lambda, but there's still lambda to the, from the propagator, lambda to the 4th on top. So, putting it all together, and here I am going to have to erase. So I'm going to have to erase this thing, because I don't have any more space.
Excuse me? Hello?
No? Not space?
Can I ask a question?
What's that?
Can I ask a question?
You can ask a question.
So here the lambda in the last line is not related to the lambda in the d by lambda, right? This is different.
This lambda?
Yeah.
I'm associating the lambda without subscript to all momenta, as a scale of all momenta, the cutoff scale of momenta. That's why I put it here with a derivative, because it's kind of a momentum.
Okay.
Okay. None of this is rigorous in any way. That's the way I'm thinking. I'm telling you. Okay. Okay. That's what I'm thinking. I'm not. If this is the logic I'm following. It might be flawed, but I'm telling you the logic. Okay. So erase. Going once, going twice, gone. So I can do exactly the same thing with the fermions and get the following expression. This guy then this horrible thing, 4 pi to the 2/3 lambda psi over lambda to the 3/2 f times lambda 2 and 2, which I will call lambda bar. So with this argument, I've managed to get rid of lambda bf as a function. The b and f dependence of this little lambda is now explicit, and I have only one overall coefficient, lambda bar. What I'm going to do now is the following. I'm going to substitute this thing here. I'll get a new expression for O. And next, I'm going to consider a general graph with several of these operators O inside it, and again use the strong coupling condition as I defined it. So again, I have no space. I'm going to put this here and tell you what I get. Okay? So I'm going to erase my O prime and my graphs, and I'm also going to erase this. I'm going to put it back. But it will reappear in a second. So I'm going to substitute then the expression I had for this lambda BF in here. And I get the following thing. First, you will notice, in fact, that the scales, the lambda phi and lambda psi, just cancel out, just go away. And they're replaced by particular combinations of lambda. So I get this lambda bar, lambda to the fourth. Oh, in the original expression, I knew I was missing something. In the original expression, I had this. Oh, just a minute ago, without erase, BF. And this is not right. I'm sorry. There's the 3/2 here that I've forgotten. I apologize. And to have the right units, there's a lambda to the fourth here that I forgot completely. So I forgot those two things. I apologize very much. This is the original expression we had. For the O prime, everything looked the same, but I also screwed up by forgetting this guy and this guy. I'm sorry. I copied wrong. But now I'm going to replace this. That doesn't affect the calculation I did before at all. See? Because I just looked at the bosons. If I had done it with the fermions, I would have found myself in trouble because I'd forgotten this 3/2. But the result I presented to you is correct. All right, so I'm going to then replace the expression for lambda BF, and the result is the following in red. This now becomes the lambda bar, just a thing that doesn't depend on B and F. There is here, instead of this, lambda, let me write like this, lambda over 4 pi. So instead of lambda sub phi, I have that. And now, and here, I have, yeah, instead of lambda psi 3/2, I get lambda, the same lambda, 3/2, also divided by 4 pi. So this is the result of getting rid of the B and D and F dependence of the coefficient in front using the argument of strong coupling. All right. Yes? Excuse me? Where are you? Left on. Okay. Yes?
So for lambda side, 150 lambda by 4 pi multiplied 2 by 3 by.
No, actually, it works out with the 4/3, with the 2/3 and everything. It's just the 4 pi. I checked. I mean, I'm happy to go with you with the calculation step by step for the fermions. But this is exactly 4 pi. There's no 4 pi to the anything there. Really, there's no. Other question? All right, now I want to consider a generic Feynman graph that has, I don't know, looks like, I don't know, has loops, has external lines, you know, for all I know, has external lines, has internal lines, you know, like this, I don't know, it has other internal lines, things like this, okay? A Feynman graph, a generic Feynman graph. And these vertices are all produced by a set of operators like this, O1, O2, O3, OV in general. Okay. And I want to estimate this graph again. And I am going to, okay, so I'm going to estimate this graph. What is this graph supposed to do? It's supposed to make a radiative correction to some vertex with one, in this case, with 4 external legs. This vertex, so the external line, this vertex will also correspond to an operator. So this is a renormalization or a radiative correction. Perhaps, let me call it like this, a radiative correction to an operator O. To O. And the vertices from a set of other operators O little v from 1 to big V. V is the number of vertices, total number of internal vertices. And I want to do my estimate in the same fashion. So what do I have? I'm going to estimate this graph. I have a factor of lambda bar, lambda to the 4th, to the V, because I have V vertices. Okay? I have a factor of 4 pi over lambda from this guy to the sum of B sub V. I have a factor of 4 pi over lambda to the 3/2 to the sum F sub V. Okay? I have a factor of 1 over lambda to the sum of D sub V. Oops. That comes out of the vertices, just the vertices. And now I'm going to estimate the loop integrations using the same thing, replacing every momentum by lambda. It's going to do. So what do I have? 1 over 16 pi squared to the power of loops. Then I have a lambda to the 4L, because every loop integration is d to the 4, some momentum. Then I have 2 powers of lambda inverse for each boson line. And these are the number of internal boson lines. 1 power of lambda inverse for each of the fermion internal lines. So IF is the total number of internal fermion lines. And now there is one more thing I want to point out. The momenta I'm replacing by lambda, but I cannot do that for every single momentum because the operator I'm looking at has d derivatives. This corresponds to d external momenta. These external momenta have to be taken into account in this calculation. Since I am taking out the external momenta, this must be compensated by dimensional reasons by precisely the inverse powers of lambda. So this is the graph. This whole thing is here, my angry graph. Okay. It looks very messy, and to be honest, it is very messy. But there are a bunch of graphs, there's a bunch of relationships that can really help us in simplifying this. I'm going to give you the relationships, and then I'm going to give you what the simplified expression looks like. Okay? So here are the relationships. First, the sum of B sub V is equal to 2IB plus B. This B is this B because this is the guy that this is supposed to do radiative corrections to. The sum of F sub V is 2IF plus F. And then we have our old friend that L is equal to I, the total number of internal lines, minus the total number of vertices, plus 1. And you will not believe what you get when you put it all together. You get that this coefficient is, this whole thing is lambda bar, lambda 4, to the V. No, I'm sorry. What do I get? Yeah, sorry. No, this is not. No, sorry. Yeah, because there's a bunch of 4 pi's. You get the following thing. 16 pi squared lambda bar to the V times lambda bar lambda to the 4th. That's a coefficient. Which is a very nice simplification. All this, I agree, it's worth going through the mess if you have nothing better to do to get this result. This is the coefficient of the original guy. This loop correction, what it does, it gives you the original coefficient times this power of 16 pi squared lambda to the V power. Okay? What's that? Yes, I have not put any constraints on anything. It's just completely, it's a completely general hand-wavy argument. Okay? So with the assumptions I've made no other assumptions. So with this thing, you can calculate a new coefficient produced by this guy for this operator.
I have worked out. Is V with all vertices or just external vertices?
No, V is all vertices. All V's are all the internal vertices. All the internal vertices. All these. In this particular graph, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 guys. Okay. 12. All right. And now, finally, the condition for strongly coupled is that this guy has to be the same order as this guy, irrespective of anything that, irrespective of the graph. And that can only happen if lambda bar is 1 over 16 pi squared, and we're done. Okay? So lambda bar is 1 over 16 pi squared. And now we're really done. So we have a full estimate of the vertices in terms of a single scale and the condition of a strong couple. The assumptions I've made originally and throughout was that all momenta are associated with the scale lambda. I've replaced that I'm going to use as a cutoff, and I replace every single integration, every single instance of a momentum by lambda, except for the external ones, giving rise to this particular factor here. Doing that, and again using again and again the condition that the theory is strongly coupled, I found an expression for the coefficient of the operator that replaced the original, in principle, independent scales by these, which are related but except to the momentum cutoff scale or the momentum scale by a numerical factor. And then considering this generic form of the operators in a generic graph, and again using the expression for strong coupling, I find a consistency value for lambda bar, 1 over 16 pi squared. And that is what I tried to do too briefly in the couple of slides a couple of lectures ago. Any questions?
So, the question is, like if you are doing a higher order correction and then if you get these different operators which are of the same order as the varied corrections, then how do you truncate?
You never truncate. No. The problem, okay, so the question is, how do you truncate? I can't truncate. The only thing I can do is estimate in this thing. And so in extract, you don't truncate, you extract certain useful information from these things. You cannot do a full perturbative calculation under control. You can't. I'm just telling you, it's not under control. Exactly, it's not under control. Exactly. So it's a strongly coupled theory. What you can do sometimes is extract some particular interesting information. Certain radiative corrections actually can be calculated. Say, you have many operators. You can calculate the running of some of the coupling constants, the renormalization group running of some of the coupling constants, using the fact that only operators that you have, I'm trying to jump ahead. If you have a set of leading operators, you can calculate the corrections running of their couplings using the effects of these leading operators only. You don't have to consider subleading operators, the effects of them.
That would be perturbative, right?
It looks perturbative, but the theory in itself is not perturbative. Only the running of the couplings can be calculated perturbatively.
Yes, if you have like a large anomalous dimensions, then this cannot be done.
No, you can't. But I'm sorry, I can't. Maybe you can, but I don't want to make assumptions. I can't.
This is just based on the fact that this is just naive dimension.
Exactly. This set of hand-wavy argument is called naive dimensional analysis because if you go through this carefully, the only thing I'm using is the dimension of the terms in the Lagrangian is 4. That's really what I'm using. That's a big thing. If you by the way, if you live in a different universe, like 11 dimensions, the factors change. Okay, the factors change. Okay, good. I mean, but you can do the same thing. Other questions?
One more question.
Please.
Like typically for loop diagrams, what is the kind of regularization one must use?
Okay, the question was, what kind of regularization does one use in loop diagrams? In actual calculations, you use dimensional regularization because it's just easier. And it has to be done carefully and as every calculation does, but usually the practical application is dimensional regularization. Some people use cutoff, some people use, which is problematic. Other people use polyvillars, which is, has its own issues. Depending on what application you want. If you want to just, get an idea of how it's going to go, use a cutoff because it's faster. If you want to get it right, use dimensional regularization. Other questions? All right, so I'm going to go back to this thing, and after one phenomenological application of of the theory. For the case of weakly coupled, I'm going to go back and talk a little bit about the formalism itself. And I've been telling you that you can dispose of operators that are, in a sense, equivalent. That is, that they are equal when the equations of motion are imposed. I know that was vague. That was on purpose made vague in my comments. I am going to make it very precise in the following slide. Or that's my intent. That's my hope. So I'm going to talk about something called the equivalence theorem. You all probably have heard of the equivalence theorem. This is not this equivalence theorem, the gravitational mass equal to the inertial mass. Not that. There is another equivalence theorem that says that the longitudinal components of the gauge bosons and those of the would-be Goldstone bosons in a spontaneously broken gauge theory are the same. That is not this equivalence theorem. Unfortunately, the equivalence theorem sounds really nice, so everybody wants to use the label. So you just have to deal with it. Remember the equivalence theorem. This is the equivalence theorem, if you wish, for EFG. Okay, so I'm going to talk that. All right. So the equivalence theorem I'm going to talk about is the following. Suppose you have your effective Lagrangian that has a light component and a bunch of other effective operators. And I've neglected to put in this lambda to the n, whatever, just because I didn't want to clutter the notation more than needed. Now, imagine that you have two effective operators such that they obey this relationship. This is an explicit relationship. You look at one operator, look at another operator, and see if there is some constant such that if you multiply the first operator by it, subtract the other operator, you get something times the classical equations of motion. This is by definition the classical equations of motion. This slight is the integration of the light Lagrangian. I am going to imagine that these guys have been ordered in a leading, subleading, sub-subleading, blah, 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 blah. These are the leading guys. If you want to imagine, you want to consider the effects of the subleading guys not listed here, and you find two operators that do this, this expression is slightly modified. I can talk to you separately about it, but let's not complicate matters more than needed at this point. These are the leading operators, leading corrections to the light theory, and I find two operators, O and O prime, that obey this relationship. Then, what the theorem says is that the S matrix, anything that you can observe, let me emphasize this, anything you can observe, not anything, anything that you can see, will depend only on this linear combination, not on anything else. It will not depend on the coefficients of O and O prime separately, but only in this particular linear combination, where this particular quantity A is the number here, this precise number. Okay? That is the equivalence theorem. Why is it interesting or useful? Well, because if every observable, and this is, again, let me try to be very clear. It doesn't mean that these operators are the same. It doesn't mean that these operators come from the same new physics. It doesn't mean any of that. What it only means is that at low energies, their effects always come up in this linear combination. The effects of these operators are summarized by how things depend on their coefficients, and the coefficient dependence is always like this. Therefore, if I set this guy to 0, I lose nothing, because there is no way of differentiating from the effects of this guy and this guy at low energies. In fact, when you measure quantities, and if I tell you this quantity always contains this linear combination, well, it is this linear combination that you will measure, not this guy and this guy separately. So you might as well get rid of this guy and measure and obtain constraints, values for this CO. keeping in mind that in fact CO might represent a linear combination of contributions. The high energy theory, whatever it is, may generate this guy, or may generate this guy, or may generate both. At low energies, you can't tell the difference. If it only generates this, well, then you will measure it. If it only generates this, you will still measure it, like that. And then you can't tell the difference. So the equivalence theorem says that operators like this, that have this relationship, cannot be distinguished at low energies. That is, their effects cannot be distinguished at low energies. If you don't look only at S matrix elements, you look, say, at things you can't measure, propagators or something like that, vacuum polarization that you can't measure in general, then you will find that C and C prime appear separately. But whenever you look at an observable, that independence of C and C prime is proven illusory. So they always come up like this. And so what one does, if one doesn't like to deal with many coefficients, is to go tediously through the list of operators you can construct and eliminate either O of O prime, whatever strikes your fancy, from the list, knowing that they're redundant as far as low energy observables are concerned. Okay, all right. So this is a result. This is the comment that I was making a little while ago. That what I'm going to do is calculating the situation where, and I forgot to change. This is the Lagrangian. I used the wrong font. I apologize. So this is curly L. This is the Lagrangian. Is valid to lowest order in the effective theories corrections in the Lagrangian. If you have high order corrections, then you have to, instead of using the light theory, you have to use the light theory plus the effective theory terms up to the one below you're interested in. So instead of having just this here, you have to do this. The calculation is the same. Actually, doing it for general K, it just introduces more complication with any conceptual advantage. And let me again super emphasize, this is a property of the light physics. This property at the low energy limit, right? Because the equation of motions that you're imposing are the light theory's equations of motion. Has nothing, provides no information about the heavy physics. It doesn't mean that somehow the heavy physics has to generate operators always in this type of linear combination or anything of the sort. Okay. It's just a property of the light theory. Now, instead of doing a full-fledged quantum theory calculation to begin with, I'm going to do a quantum mechanical calculation. Yes. He's younger.
Again?
Yes.
Can you go to last time? So in this relation, is there any limit of energy both sides, let's say E equals to something?
The question is there any limit in the energies in which I am doing this calculation? No, this is supposed to be an operator identity. So you have operators, you know what, I might as well do an example. I'm going to erase here and give you an example, because otherwise I'm just choking in empty space. I'm going to do a very simple case because it's useful. Your light theory is just a scalar field. It's a lambda phi to the fourth. Okay, it's 1 d phi squared minus 1/2 m squared phi squared minus 1 over 4 lambda phi to the fourth. Okay. Okay. the equation of motion. Minus 1/2, yeah, that's not even true. Equation of motion. Okay. Now, let me consider one operator that has dimension 6, just for fun. Okay? Just operator. So, operator dimension 6. It's dimension 6. Okay? Now, let me make my life simpler. Okay? 3 and 1. I like this one. That's right, so I'm not going to put 1 here. Okay? And the reason for that is I'm going to write this using this guy. Okay? Bear with me. So I can write this as phi cubed box plus m squared phi plus lambda phi cubed minus things. Minus m squared phi 4 minus lambda phi 6. I didn't, okay? I am going to call this O. No, I'm going to call this minus lambda O. Minus lambda O plus lambda O. I'm just going to call it plus lambda O. No, minus, yeah. And I'm going to call this guy, in fact, O prime. O. Pardon me? Lambda will become A. I mean, bear with me, okay? Lambda, just wait. Wait. So I've proven the following thing. Oh, proven. I just, it's made the simple calculation says the following thing. That this is phi cubed minus, I'm going to put like this, minus delta okay? So what the theorem says is that I can place, whenever I have this guy, I can replace it by this guy. This lambda plays the role of A. This plays the role of the curly A that I had. And what the theorem says, again, is that if you have a general effective theory, you write all the dimension 6 operators, you come to this guy and say, ha, can get rid of the guy, and I replace it by these two guys. This term is innocuous. It's a renormalization of the phi to the 4 term in the Lagrangian. This is a bona fide dimension 6 operator, okay? Does that answer the question?
One more thing is that, let's say, maybe it's not a very question, but let's say, if we have any nonlinear relation between O and O prime, is there...
Say again. Use microphone.
So if there is some non-linear relation between O and O prime, let's say, then is it infer anything?
No. If you have AO is O prime minus O prime cubed equal to something like that, is that what you're thinking?
Yeah.
No. Well, in reality, what happens? If it's AO minus O prime cubed, I called O prime cubed O double prime, and I now have AO minus... But if you have a relationship of the form AO plus BOO prime plus CO prime or double prime or some other complicated thing involving O and two other operators or something like that, this theory doesn't apply. This is it. Okay. There's nothing more beyond this. This is going to be it. Okay?
Yeah.
I'm sorry, your question?
No, this is a very nice question. Like this is basically this decoupling kind of.
This is different from the question whether this is related to decoupling. This is different from decoupling. I'm I'm not getting rid of operators. This is I'm assuming decoupling, but I'm not getting rid of operators. The only thing I'm saying is that at low energies, if you have this guy and you have this guy, you cannot tell them apart. The effects of each are the same. And on that happy note, I will finish. This lecture. I will come back and give you the example using quantum mechanics, which is, I hope, familiar to all of you. And I think it provides a simple gateway and rather painless to how the equivalence theorem works. More questions? All right, then I'll see you this afternoon. Thank you.